My name is Lauren Dow. I'm the Communications Coordinator for the National Road Research Alliance, and I want to welcome you to the August edition of Research Pays Off. A couple reminders here at the beginning to keep yourselves on mute. That will just help prevent any feedback or unwanted audio noises happening. If you have questions during the presentation, please feel free to write them into the conversation box, and Eyoab will get to those at the end. We have a few more months already scheduled out for Research Pays Off in September on the 15th. We have one of our invited speakers presenting her original planned talk for the pavement workshop this year. We will have Cheryl Richter presenting on the Federal Highway Administration's Turner Fairbank Highway Research Center and Pavement Research. And then on October 20th, we will have Ben Worrell and Steve Hendricks from MnDOT talking about their online systems for test section tracking at Bin Road. So we've got those already planned out, and you can find more information on the Research Pays Off website. Today's session will be recorded, and you'll be able to find that on the National Road Research Alliance YouTube channel, and links to the video will also be on the Research Pays Off webpage. And I'm trying to think if there's anything else related to the NRRA that I want to share. We have announced to the groups who have been chosen for the call for innovation. Those emails went out last week, so I'm working on getting those pages up and onto the websites. Today we have Eyoab Zegeye, who is here to talk about the road doctor and his research with that as part of work he does with MnDOT and I think various other pooled fund projects, I'm assuming, but I'm sure he will cover that more. So welcome, Eyoab. I will turn it over to you. And if you could make your presentation full screen, I think that would help us.
Oh, it's okay. Let me. Can you see now?
Not quite yet.
Lauren, can you see?
Not quite yet. It's loading now.
It's loading, okay.
There we are. Perfect.
Okay. Thank you, Lauren, for the introduction. Good morning, all. Good morning, everybody. Thank you for taking the time to tune in this morning. My name is Eyoab Zegeye. I'm a research scientist at Minnesota Department of Transportation. I'm very happy to share with you our experiences and the lesson learned on using the road doctor for the evaluation of pavements affected by severe crack-heaving, also known as tenting. Before I do that, though, on behalf of the group of people who work on this project and myself, I would like to thank NRRA for giving us the platform to share these findings, these ideas with you all. Thank you. I'm trying to move to the next slide here. Isn't that moving to the slides? Okay, here we go. The work that I will be presenting today, it was accomplished through numerous collaborations, meetings, discussions, and consultations with my many colleagues at the Office of Material and Road Research of MnDOT. I would like to thank them all, and I would also like to thank the leadership for the continuous support and research on innovative technologies. It's such a blessing to work in such an environment, and especially now that we are working all from home, I appreciate more their collegiality and friendship. And I would also like to acknowledge the work, the people involved directly in this project: Thomas Calhoun, Steve Olson, Eddie Johnson, and my mentors and managers, Dai Chong Tao and Jeff Brunner. I also would like to thank MnDOT District 1 for helping us, for coordinating for all the field testings discussed in the slides. Crack-heaving or tenting, for those who don't know, is a transverse crack-heaving, is a pavement distress condition that affects primarily bituminous surface roads built in cold regions. For those who want to know more about crack-heaving, please do contact me through email or phone. I would be able to give you a more comprehensive literature review. But here, just briefly, just to explain what it is, it's a pavement condition which is caused primarily by the presence of moisture in the base aggregate, freeze-thaw cycles, frost-susceptible aggregates, de-icing chemicals, cement-treated aggregates, and lately we've seen also that roads built using rubblized concrete bases are prone for this type of pavement distress. The main driving force is, I try to explain here with these two simple models, simple scheme. It's like in winter when you have moisture in the base aggregate, basically you have this frost heaving action that moves upward and lifts the pavement on both sides of an existing or new transverse crack. And so by doing so, it creates a peak similar to that, to the pointed tops of tent. So that's why the name comes from, the name tenting comes from. Again, here I give you just a very simple description of what it looked like in the real world. Basically, you have these tented cracks with different spacing between them and different height that can cover long stretches of area. And the main impact of this type of tented crack is that they impact the ride quality and comfort of drivers. I put here a video just to show you how bad it's when you have a vehicle driving over these tented cracks. It's basically it endangers the safety of the drivers. I don't know if you are able to see the video. I see it's very slow to do the internet, but it's very hard on the vehicles, and it endangers the comfort and the quality of the ride. But it's also good to know that it does not affect only drivers. It affects also local inhabitants. Yes, one thing that we learned during this testing in Duluth area in District 1 is that this type of pavement distress affects also local inhabitants. The reason for that is that many of these highways in the rural areas, they are also designed to serve for mail delivery boxes or for school buses. In fact, you do see some kids waiting for school buses sometimes. And what happens is that drivers, when they are driving on these very rough roads, they try to avoid the tented cracks by driving on the shoulders. This endangers the local inhabitants. Another characteristic of this type of pavement distress is that because it's very visible, it's one of the most complained pavement distresses. In fact, it's very common to see headlines on the news on prime time about tented roads that have been repaired, and then again they still show up winter after winter, this type of distresses. Talking to engineers that have worked on this issue for so many years, one thing that you learn is that there is no one-size-fits-all treatment approach. The phenomenon is very complex and it's unique to individual projects. However, they all know that we do have some possible solutions, from as simple as grinding to level the tinted cracks to completely removing and replacing the base aggregate, and by that also the pavement structure. So we do have those treatments that we think could work. What is missing is that we don't have, first of all, we don't have an agreed understanding of the mechanisms that produce tinted cracks. Then, most importantly, we don't have an established rapid testing and evaluation methodology for pavements affected by tinting. And then later on, we don't have a structured approach for selecting the best solution for an individual project. So if you don't have these tools, it's very hard to choose the proper treatment. And when you don't choose the proper treatment, as it happens more often than we would like, you repair a road and then it comes back again next year and public is complaining even more. So this is the brief introduction to the crack-heaving tinting problem, and especially from the point of view of Minnesota. So because of this reason, at District 1 office brought the issue to the attention of our office, and it provided us with a long list of roads affected by tinting that indicated different severity levels based on visual inspection, but also based on the complaints that they were receiving from the public. I know it's very small here to see, but you can see here some of the roads here, like US 169, one of the most complained by public. Just to give you an idea, our office is located in the metro area in Maplewood, and the roads that we are talking about, they are all in District 1 in the northern part of the state. So the Minnesota, the District 1 office, they provided us this long list of roads, and then they asked us if there is anything that the road doctor can provide to support the treatment decision-making process. For those who don't know, for those who are not familiar, the MnDOT Road Duct Survey Van is an advanced survey van composed of equipped with many advanced sensors, non-destructive sensors. In my view, the three most important items in the road doctor are the three data acquisition, data controlling units, and the cam link from Node Scanner, the SER30 from JSSI, and the geoscope from the examiner. So the cam link controls most of the sensors, including the positioning and navigation system, GPS, IMU, and DMI. 2 video cameras, high definition industrial video cameras, high resolution accelerometer, thermal cameras, and the LIDAR laser scanner. While the SER30 controls the 2 horn antennas depicted in the picture here, the 2 horn antennas, I don't know if you can see my mouse, and then the ground couple antenna, which is basically in front of the vehicle. I will speak more about these 2 antennas, their differences later on, and then we do have the geoscope 3D radar 3D radar antenna. As a brief timeline, we purchased all the sensors for the van from Road Scanner in 2018, and then we assembled and installed all the sensors in the survey vehicle through a very successful collaboration between MnDOT staff and a local contractor. In 2019, it was completed. We went through a training and verification with Road Scanner, and then since then we continued learning the system. We developed some implementation plans for projects. We did some trial field tests on I-90 Adrian, Minnesota, I-94 St. Paul. And then in 2020, we started this project, the District 1, which is one of the most comprehensive projects that we have taken so far, the District 1 tenting issue. We are also running a moisture monitoring test. And of course, in 2020, we had also COVID-19. But in the next, we have some other items that we would like to investigate in the coming years, including validation of the tenting parameters that we proposed in this study, and then moisture monitoring, stripping, and some project scoping applications. Here is below. I put two pictures that shows you gives you some views of the survey van. We can run it in two different configurations. One is using the 2 horn antennas and the ground couple, the thermal camera, and the video cameras, which are inside protected, isolated in this box. And then we have the LIDAR laser on the back of the survey van. Here, the second configuration, we have the 3D radar. Everything else is the same. Here is just to give you some views, first, to share with you some rear and side side views of the van, how we store the equipment inside this workstation, how it looks like when we are testing, especially when you're testing during nights. So back to the tenting. So when District 1 approached us with the tenting issue, from our perspective, we were very happy because this was a great opportunity to test the road ductor in winter conditions. So, and then our intention or our objectives, if you will, were to test it, to develop or explore testing parameters that can be used to detect, measure the tented cracks, and then based on these parameters to develop a criteria for rating and identifying critically tented sections. And then lastly, draft a reliable testing methodology for evaluation of pavement affected by tenting. The approach we took was obviously, it was very difficult to test all the more than 20 roads that were proposed by District 1. Instead, we chose to target a limited number of roads with different tenting severity levels. And then we decided to use all the available sensors and to collect data according to this plan here. First, initial collection in winter 2019. And then monitor if there is any change between winter and summer by testing in summer or fall 2020. This is going to happen very soon. And then in winter 2020, validate the test parameters that were proposed in this study. And so the idea was, first of all, to collect data with all the available sensors and then look at the data, explore if we can find some parameters that can characterize the issue and that can be used to basically describe in quantifiable manners the issue. Here are the rows that we selected for testing. As you can see, I colored in red the most severely tainted, most complained by public. And then we have in yellow the ones that showed moderate level of tainting. And then we also included Minnesota 37 here in green, which was recently rebuilt. So it didn't show any major problem with tainting. We kept it there for control to compare with the others. The total of 100 miles of road was surveyed during 2 days of testing. The target testing speed was 30 miles per hour. This was a balance between the different requirements of the different sensors, and also because we had the ground couple antenna, GPR antenna, very close to the surface, so we didn't want to run into problems there. And because of this low speed, and because we were testing also highway roads, it was required that we coordinate with traffic control and that we coordinate with the winter plowing plans of District 1. And District 1 has been very crucial, very helpful in achieving this test in a successful manner. Also, we chose the 2 dates, two very cold dates for testing. The reason for that is we wanted to ensure that the tainted cracks were formed when we test This was not planned but I think it's mostly by plan, not by plan, by luck. We end up testing on 2 days on the coldest week of the winter. The temperatures were below 19 degrees without no wind chill. So this was good because it ensured that tinted cracks were formed. However, unfortunately, or maybe as a first lesson, we found out that the freezing temperature, along with the rough rides, end up damaging some of our cables, sensor cables, especially the cables which were outside of the van. So this ended up compromising some of the data that we collected. So not all the data well done data processed because they were compromised. But at least this was a first learned lesson. We need to take more care on choosing the proper way of testing when we are especially going on very rough roads and in very freezing climates. As I indicated before, the plan was to take all the sensors and test them. We used all the sensors. We end up not running the 3D radar because the very cold temperature and the long time of testing made it quite impossible for us to go back and then test again the 3D radar, especially because by the end of the 2 days, we already knew that we had 2 cables broken. So for now, we kept it with the ground coupling. This was a kind good because for us was, first of all, this was where we learned what we can do, and ground couple it give us a one-dimensional view of the GPR results, and then going forward we can build on that. And once we've completed the data collection, we processed, the initial processing was done using the road ductor software. The road ductor software is a very robust software. In my view, the main advantage of this road ductor software is it can link different data sets, and then you can also visualize the data linked together. I put here 2 views of the road ductor. You have the video camera, you have the LIDAR data, the roughness data, thermal data on the top. On the below you have video, map, GPR data. So I will try just if it shows. So here you can, the video is moving. I don't know if it shows on your end, and as the video is showing, the map as the video is moving, the map is moving, and so now you can exactly, it helps you to investigate more closely when you have anomalies. And then another important thing that the road ductor software does, once it processes the data, the GPR data, the IRI data, everything, it then outputs tabulated files that can be further investigated. The views can be shared with people who have road ductor software viewer. But for our purpose, we wanted to investigate further the data. And so we took out the outputted files, and then we further processed them using some Python algorithms, because the data was so large to process in Excel. So what we did then is we divided all the data from each road into smaller lots, in lots of one quarter mile. And then we plotted and analyzed each lot separately. Here I give you an example of, for example, we have on the top the thermal data, the LIDAR data, the profile measurement, the IRI data, the GPR data, and another GPR data, MDI, I will discuss later. So this gave us the opportunity to look closer at the data, and then to start to exploring relevant parameters that can be used to measure the tinted cracks. And now I will go on by explaining how each of these data, how we looked at each of these data sets. So just to wrap up, we end up testing over 100 miles of road, but only 47 miles of roads were not compromised, so we're analyzing this data. This meant that we end up looking at more than 300 loads one by one, or at the videos, at the GPRs, and trying to find out which parameters can describe or characterize the tenting issue. So the first is the video. We were very happy with the videos. We had two videos. I'm showing one of the videos. One of the video was pointed toward the road. The other is pointed toward the ditch. Here I'm showing the one pointed to the road. And we were very happy with what the video was showing. We found that the video is very good for visual inspection of the roads. And it was essential in identifying sections which were heavily affected by tenting. And importantly, it also gave us an indication of the degree of tenting, because you could see the vibration on the vehicle and the bouncing of the horn antennas in front. This is a video. I will try to show you, but it will be very slow. Probably you will not appreciate how much the vehicle was bouncing when you see the tenting. So in that sense, it was a very good tool for us to understand and somehow read the roads. And what another good thing that does, whatever parameter we came up with, this was a way to verify, the videos were a way to verify if the parameters, the numbers with the parameters, if they make sense. The second data set came from the LIDAR laser. The LIDAR laser, it's basically we have the laser generator that emits a laser beam toward the pavement surface and records the reflection. Some of the items recorded are the travel time, the distance between the laser generator and the targeted point, the angle of beam, laser positioning, strength of reflection. But the most important thing is that then when you have all these items, you can derive the X, Y, Z coordinates, the local coordinates that can be transformed to longitude, latitude, and elevation. And then based on this cloud data, you can reconstruct the surface of the roads. Here I showed one of the picture is the LIDAR emission plan view. This is the view of one lane of the road. You can see here. You can see that the LIDAR revealed reasonably well the transverse cracks. We looked also, we tried also to see at the elevation data, if you could use the elevation data to measure the tented roads, but because of that effort was not successful because of the accuracy and density of the data. But anyway, we were able to see from the LIDAR all the transverse cracks. What we were not able to say if all these transverse cracks were tented or were just transverse cracks. So the next data set we looked at is the thermal camera. The thermal camera is becoming very popular lately because it is very useful in detecting surface defects and anomalies that could be signs of underlying issues. The thermal camera, they measure the surface, the infrared thermal camera measure the surface temperature. The assumption here is that defects or anomalies possesses different thermal conductivity and heat retainage capacity compared to the surrounding bulk area. So if you have an issue, especially in this case where we think that some of the issues are related to moisture, then definitely an area with more moist or more salinity or more ice, it will show up compared in contrast with a drier, less affected section. So, because the variation of the temperature within the lots and within the rows were very large, it was required that we do some filtering especially to enhance and reveal the short wavelength temperature. We used a normal anti-smoothing filter based on moving average of base 16 feet, and here you can see in the charts the blue ones are the short wavelengths and the gray shaded are the long wave So when you, this is just a temperature measurement in one line, one profile. But if you take all these profiles, about 300 profiles for the entire width of the lane, you end up with these two heat maps. So now, please remember these two sections, because I will be talking about I will use them again as an example going forward. We have section A, which by looking at the videos and looking at the LIDAR data, it showed very little tinting. On contrast, section B, it was extremely tinted section. So now when we look at the thermal data set from them, you can look at the section A on top. It shows less thermal segregation than section B. Again, the section B, it also shows these anomalies, the defects that they are occurring almost at regular intervals, almost close to the matching very closely the transverse cracks that we've seen in the LIDAR data or the video data. So this was already another thing. It is telling us when you have these warm areas. I'm talking to my supervisor and mentor, Mdi. He also was mentioning that this red area could be also one of the plausible reasons. Well, could be, yes, you have tinted area, cracks, and then probably when you put salt on them during the de-icing, probably they will retain the salt more than the others, and that could be one of the reasons. Regardless of the reason, we were happy to see the thermal segregation is showing us when you have extreme tinting compared to no tinting. Going forward, we look also at the GPR data. For those who are familiar or not familiar, GPR is a non-destructive technology commonly used for pavement subsurface investigation, like layer thicknesses, anomalies, defects, utilities, dowel bars, void in asphalt layers, etc. I will try, just for the sake of the discussion, I will try to give a brief, simplistic explanation, description of what is the technology. So please bear with me and forgive my simplicities in doing this. So the concept consists in transmitting electromagnetic waves, pulses into a medium. So you have you transmit, and then you record the back reflected energy. And the idea is basically the emitted pulse, it propagates through the medium, and then every time it reaches a medium which is different, which has different electromagnetic properties, it reflects back part of the energy, and part of the remaining energy, it continues to propagate in the next surface until it attenuates. So every time there is a significant contrast between different mediums, you get back the signal response, you get back the reflection back. So this is what generally looks. This is this is a horn antenna idealization, very simplistic. But just to give you an idea, this is what the response or signal response, GPR signal response looks like for one static measurement. So when you have static measurement, you measure the time of arrival of the response in the y-axis, and you measure also the strength of the reflection. So here, for example, when the pulse reaches the ground surface, you have the ground reflection, you see, and then when it reaches the interface between the AC and the unbound aggregate, you have another significant response here. So knowing some properties, you can measure the thickness here, or in other cases, you would know that there is a huge contrast of two different materials in this case. So this is a static measurement. What happens when you move forward with your GPR equipment is that now, instead of one trace, you have thousands of stacked traces. When this hundreds, here I have only 10 or 20 stacked traces, but when you have more of them, then you end up with this GPR profile that you can, most people use binary gray colors to show them, but you can also use different colors. But this is just to give you a brief explanation of what GPR technology is. And it's important to know what type of GPR you're using. On the giving for the same pavement structure, for the same pavement material, another important variable is the antenna frequency. So based on generally, in a simplistic way again, when you have larger antenna frequency, you have higher accuracy, but you lose in depth of penetration. And vice versa. When you have lower antenna frequency, you have lower accuracy but higher depth of penetration. That's why we have two different configurations or three different configurations of GPR antennas. We have the ground couple antenna, which is a 400 megahertz, which is suitable for investigating the base, sub-base, and probably some part of the subgrade, depending on the pavement condition, depending on the material, depending on the moisture condition, depending on many variables. And then we have the horn antenna to 2000 megahertz that are more suitable for the top layer, or probably for the top asphalt layer, because they have higher accuracy but lower depth of penetration. And then we do also have the 3D radar frequency. 3D radar antenna, which operates in a different technique, which is called step frequency. Basically, it collects data in a wide array of frequencies from 100 to 3000, and then during the data processing, it chooses the responses with the highest resolution. As I say, as I indicated before, for this study, we end up using mostly the ground couple data. We intend to build on it, and then whatever we learn, move it to the other GPRs, especially the horn antenna and also the 3D radar, because then you will have a full picture, full lane width picture of the issue. So the data, the GPR collected from the ground couple data was processed first with the road doctor software, moisture modeling from road scanner. The road scanner moisture modeling gives you two products for moisture. One is the moisture map, and the second is the moisture damage index. I will try to explain what these two things do. And first of all, the assumption is that when you have the same pavement, and when you have for the same pavement, for the same structure, for the same material, but then you have one spot which is moist or frozen and one spot which is dry, then this will show in the GPR signal responses. And then what the second assumption is that the difference in moisture is reflected in small changes in signal frequency content. And moisture impact are measured, obviously, at the frequencies close to the antenna frequency. So whatever is far from the antenna central frequency, it can be considered as a noise. So and based on this assumption, you can derive some GPR parameters that can be used to measure the moisture activities in the base aggregate. So here is the original, for example, just to give you an example, this is the original measurement signal frequency and in time domain. And if you convert it through frequency analysis to its amplitude and frequency, then you can see that the same signal has many frequencies. So the next step is, oops, what happened? Sorry. So the next step is to filter the frequency responses with very close to the antenna. In this case, we chose to filter out from 50 to 400 megahertz close to frequency, and then you get this red signal response. And based on, once you have this filtered, what road scanner has done, we don't have yet a final official manual or paper on this, so don't quote me, but just in the understanding is that then you average the reflections on a fixed window length of the signals. And if you do this for all the traces, you end up with a profile measurement where you can, looks like this. So again, these are the GPR parameters derived from the GPR data that are assumed to measure the moisture activities in the pavements. I'm again using the same section A and sections B from before. As we mentioned, the section A showed little or no tinting, while section B showed it was extremely tinted. Here we were very happy to see, in fact, this was also reflected on the GPR data. On the top one, yes, you do have some moisture activity, but not as traced, as significant as the one shown in the plot below. But another thing we showed that these moisture activities, these huge marked moisture activities, they were again occurring at a regular interval and then very closely matching the transverse cracks. So whatever it was observed in the surface, now there is also something going on beneath the surface. So now we had the LIDAR, the video, and the thermal telling us, providing us good information on the surface, and now you have the GPR telling you, also confirming us that there is something going on beneath those tinted cracks. The MDI moisture model is basically, it takes these GPR parameters and then it relays them to moisture contact values. So this relationship was, our understanding is that this relationship was developed through laboratory experiments using finished aggregates. So we didn't know if this would work for the Minnesota aggregates. So for now, for the time being, we chose not to use the MDI, not to consider the MDI for this study. Instead, what we are doing is that we are working on a new project, ongoing project, that we are trying to calibrate, verify the MDI on Mill Road test cells. As you know, Mill Road, we have so many pavement cells, pavement test sections with different structures. All of these cells are instrumented with different sensors, including moisture sensors, and the temperature sensors are varying lengths. And we've been monitoring this data for like more than 20 years. So we do have moisture data. What we're doing now, as I show here on the chart in the right, for example, how the moisture varies from winter to summer. So what we are doing now is we are monitoring these cells using also GPR and also FWD to validate the MDI and to see if we can use the GPR to monitor the moisture activities in the pavement. So far, we have some very good, promising early results. For example, here on the left, I show the charts from the FWD data. As you can expect, in February, when base is frozen, the pavement is very stiff, so the plate deflection is very low. And then in early spring, it jumps up, and then it kind of stabilizes in this plateau. This is for all different cells with all different pavement types. But also we observe very encouragingly that the MDI is showing a very good trend, very good relationship with both the back calculated base modeling and also the MDI parameter that road scanner proposed. So we are continuing with this monitoring. We plan to monitor from winter to winter, and but these are very encouraging results that will enable us to use GPR to kind of have a sense of the moisture activity in the pavement without having to use moisture probes every time. Back to tinting. So far, we've seen that the video, LIDAR, thermal, and GPR provided good information, surface and subsurface information of the tinted cracks. What they didn't provide so far is a parameter that can be used to measure the frequency, the strength, and the frequency of the tinted cracks. We don't have a number from this surface. So because of that, we continued exploring the data more. Here, the plot shows, it was a nice plot here because it shows the capability of the data fusion, the ability of the road doctor survey and the road doctor software to link all this data. And if you link them, you can see wherever you have transverse cracks, you have also these thermal segregations. And then beneath some of the transverse cracks, you have also significant moisture activities as derived using the GPR data. So this fusion, this linking was one of the important things of this study. So we continued looking at the data, but we looked at the profilometer data. In particular, first we looked at the roughness data, the International Roughness Index. As you know, the roughness index is derived from longitudinal surface profiles and the vehicle acceleration measurements. This is commonly used to check the roughness of the pavement, so it's a very popular tool. But we found for this purpose, it is IRI value are very useful to compare sections from the same pavement tested at the same time. You can compare section A and section B, or you can compare the evolution of tinting between winter and summer. But you cannot really use it to measure tinting because whatever the IRI has, the roughness has many contributing factors that it is very difficult to just extract the contribution of the tinting. But here you can see section A and section B. As indicated before, section A showed very little to no tinting, while section B had very extreme tinting. And you can see here, I put on the right just one to give you an idea, a scale of IRIs, how we commonly measure them. So basically the section A is falling on almost a new pavement, 2 to 4 IRI millimeter to kilometer, while the second one is almost in the edge of unpaved road. So this is how bad is tinting on the IRI. But again, IRI has also other contributing factors. So the next step, what we did is, this is something that we did not start. Well, actually, this was very well studied and very well applied by our colleagues in Canada. Especially, I would like to reference this paper, Evolution of Pavement Winter Roughness. They use the longitudinal surface profiles to measure the tinting. So we applied the same technique. The only difference now, we had also other data to back up whatever we are measuring. We have LIDAR data, GPR data, video data to match up, back up, and verify if these parameters were measuring. But what are these parameters? These parameters were derived from the longitudinal surface profiles. As you know, longitudinal surface profiles are composed of long and short wavelengths. The long wavelengths are generally linked to issues in the subsurface layers like differential heaving, settlements, while the short wavelengths are due to distress observed in the surface, or they are also responsible for intense vehicle vibration. So the idea was to again use the anti-smoothing technique to remove the long wavelengths and then to reveal and extract the short wavelengths, as I have shown here in the picture. What was good about this technique is that then it allows us to come up with an automated way of picking those peak values, and then also to measure the spacing between these peak values and see if these two parameters, now what I call here PHV and the SCBP, by PHV I mean peak height value and then spacing between peaks, to see if this could be used to characterize and describe the tinting. And we were so happy to see that those peak and the spacing were matching very closely the other data. So the only difference, what we added here, our contribution, was that linking this peak and spacing values to the GPR LIDAR and confirm that whatever we're measuring is close to something which we already have seen in the other data. We were very happy, encouraged by this finding. Why are these two parameters important in my view? These two important, they are important because now we have numbers. We can assign a number to the tinting issue. This we can quantify and characterize the issue. But we can also do more. We can also develop a rating criteria. For example, we try to look at the rating criteria based on the IRI. we found that obviously because both parameters, both peak and IRI are, for example, derived from the surface profile, they had a very strong correlation. Linear correlation, proportional correlation. While the other spacing and the IRI, they have also a very strong correlation, but in this case, inverse correlation. So what this allows you to do is, for example, if you want to, you can choose what is your acceptable IRI limit. For example, in this case, if we choose 175, then you find the corresponding acceptable peak height values and spacing between the tenting cracks. So by doing this, it means then you can decide, okay, if I have average peak heights below 0.12, I am in okay zone, or if I have spacing between tenting above 40, I'm in okay zone. This is a comparative way. Though you can also use some statistical analysis when you have a pool of roads that you tested. Then you want to decide which one to start where to start the work with. Then you can do some statistical analysis. In this case, we used the 10th and 90th percentile to find what are the height value and spacing value that leads to severely tented sections. We found, for example, on this case, or for this example, of course, because this is statistical analysis, is very associated to the data that we have. It may change if I change the data. So, but for this data, 0.17 height was a limiting factor. And then for spacing, when you have spacing below 28 was another limiting factors. So if you use, for example, these parameters, then you can create your priority ranking. When we did that for the roads that we tested, we confirmed that US 169D, again, as I explained, it was one of the most complained roads by public and by indigenous in District 1. We found out that that road was also one of the, based on these criteria that we just proposed, you find out that it was one of the severely tented roads compared to the others. On the contrary, Minnesota 37, the one that we chose just for base control, it was one of the least affected by this tenting issue. And then you can also do one other important thing. You can then use these parameters to map them in a geographical map so that you can identify where these issues are more persistent, more seen. And then you can locate them and then also measure the extent of these sections. And in my view, this could be a very good tool to provide to the engineers so they can go on these sections and do some additional forensic investigation to find what is the proper solution. So just to summary, the road ductile survey was found suitable for evaluation, so pavements are affected by tenting. However, care should be taken when operating the van in rough roads and extremely cold condition. The video, LIDAR, thermal GPR, and IRI data provided important surface and subsurface information of tented roads, but did not provide quantifiable attributes. On the contrary, the longitudinal surface profile measurement provided two promising pavement tenting parameters for measuring the height and spacing between the tented cracks. The validity of these two parameters, PHV and SCBP, was verified by examining video, thermal, LIDAR, and GPR data. An ongoing research at MnDOT for estimating the moisture content in base aggregates from GPR data is showing good promise. Validation, verification, scaling up testing to be conducted soon. So thank you all for your attention. And usually I would stop here, but given the new working conditions, I would like also to thank my very understanding three office mates, my two kids and my wife, that here they are helping me preparing this report. So again, thank you all for your attention. If you have any question, I will be happy to answer.
Thank you so much, Eyoab. Yeah, we just have a couple more minutes before the top of the hour. If you have any questions, feel free to unmute yourself and you can ask them, or you can feel free to type it in to the chat box.
Hello, if I can, this is Timo Saarengeto from Finland and from Road Scanners. If I can ask one question?
Absolutely. Thanks for joining us.
Okay. Thanks. And first of all, Eyoab, an excellent presentation, and you have done good work.
Thank you,
Good
Timo.
work. Just a few comments. First of all, this tenting, it's really interesting, and this tenting problems are also coming to be more and more problem in Finland and Nordic countries. We don't know yet why they are now accelerating, but we are facing the same issue. Not as bad as you guys have, but still they are. And about the MDI in general, what you have been seeing here is we have been doing winter testing, quite much winter testing also with MDI in Aurora, this autonomous driving test track in the northern Lapland. And we have got over there also Perco station sensors with the moisture sensors, and we've been calibrating, and we have got excellent correlation between the moisture content and everything else. And in when you are talking about MDI and GPR data, what you are actually measuring in the winter time is the amount of unfrozen water in the frozen ground. And that is what you see in this field. Basically, you see the ice lenses over there, which are always containing this unfrozen water, and in that way it matches excellent your finding with our findings.
Very nice.
One issue anyway, what I'd like to ask also is that you said that you had a problem with the quantifying attributes on how severe the tenting is, and you had to use profilometer data. But Road Dr. Van has also this 3D accelerometers.
Yes.
And we have been using transverse crack classification from this 3D accelerometer data in concrete roads and also in transverse crack. And there's one master's thesis made for road scanners for that. But how you do that is that you are filtering all the longer frequencies out on the accelerometer data than 1 meter or 3 foot in USK. So and you calculate only the very short wavelengths and the amplitude. And this amplitude seems to be matching extremely well. We've been doing this also in couple of cases in US, also on concrete road, when you have a joint repair analysis. So that could be a one issue. What you could try and just one comment that please.
If I may, Timo, first of all, thank you very much for staying up and for these excellent comments. But you're right, I need to clarify, maybe I didn't state it during the test. The profile measurement were obtained from the 3D accelerometer from the road data. All the data presented were from the road data. Yes, you're right. In fact, we use that. The only different thing is that we process them outside of the road data software. But yes, we use the data from the 3D accelerometer.
Okay, good, great.
Profile. Yes. Yes,
great.
But
great,
I will you gave us very good feedbacks. I would like to continue follow up this discussion with you, since you are working on the same type of issues, and see if we can interpret better our results by your help.
Yeah,
thank you very much.
Yeah, thank you.
We do have a few questions in the conversation box if you want to pull that up, Eyoab.
Oh, okay. So. Thank you. But what type of sensor were used for the moisture data? From what type of sensor were used for your moisture data? we use the GPR derived parameters, and also we use the moisture sensor that are, I don't know if you are referring to the mirror cells. We are using the moisture sensors that are embedded in the test cells in those cells 127 to 728, 188, and 189. I believe they are moisture, the dielectric moisture sensors. Again, Ken Mazer, thank you. Can you comment on what you have learned from the GPR LIDAR and IRIs that you didn't already know from the visual and profile measurement? Well, what we learned is the visual measurement was a good confirmation, but from the LIDAR, specifically from the GPR and the surface profile measurement, now we can quantify the tinting. We can measure the tinting and give numbers to the tinting issue. I hope. I hope that answers the question to Ken Mazer. Yeah, these were the, I don't see other questions, Lauren.
Yeah, it was just those couple ones.
Okay.
All right, well, since we are at just a little past 11, I think we will just wrap it up. Again, thanks, Eyoab, for that presentation. Thank you to all of you for joining us. And this has been recorded and will be available online within about a week if you need to refer back to it. I think that's all we have. So everyone have a great day.
Thank you.